Hello learners, welcome to Dr. D.Y. Patil Vidyapeeth's Center for Online Learning. I am Professor Dattatray Katore and you are studying with me Statistics and Quantitative Techniques. In this video, we are going to learn linear programming, formulation and graphical solution to linear programming problem. So this is unit 8 of your course Statistics and Quantitative Techniques. What is the motivation of linear programming problem? So why linear programming is such an important topic in your syllabus? So a lot of problem can be formulated as linear problems. So there are many business situations which can be solved using linear programming problem. There exist efficient methods to solve them. So by using the linear programming problem, we can find out the optimum solution, the efficient solution, right? Or at least give good approximation. So if the optimal solution, efficient solution is not there, so linear programming problems is a very handy tool to arrive at a good approximation to optimal solution. Solve difficult problem. So we can solve different types of problems by using the LPP, that is linear programming problem. The example is original example given by the inventor of the theory, Danzig. So best assignment of 70 people to 70 tasks. Suppose we have to assign different people to different tasks. In such a situation, linear programming can be used, and this is for the first time used by the Danzig while assigning 70 people to 70 different tasks. What is linear program? So optimization problem consisting in maximizing or minimizing a linear objective function. So there can be different objectives of different organization, such as maximizing the revenue, maximizing the market share, maximizing the output production, maximizing the profit. So these are the different outcomes. Apart from that, there can be objectives such as minimizing the cost, minimizing the expenditure, minimizing the time. So this can be the different types of objectives every organization tries to achieve. Right. So when these objectives can be formulated in the form of linear equation, then such objectives become linear objective functions. There are n decision variables. So there are variables which can affect the objective of the organization. So these variables are called as decision variables. Subject to set of constraints. So there are some limiting factors as well as. So limiting factors means there can be availability of resources constraint, limitations on the availability of different resources, machines, men, etc. So these are also expressed in linear equations or inequations, equalities or inequalities. So we have objective function, right, which can be objective such as maximizing the profit, which is expressed in the form of linear equation. It is called as linear objective function. So this linear objective function consists of some variable in x and y, etc. And these variables are called as decision variables, and there can be some constraint, that is the limitations on the availability of different resources. They are also represented in the form of inequalities and equalities. Originally, the linear programming is used in military context. Program means resource planning. So program is a problem. Terminology due to George B. Danzig, inventor of the simplex algorithm, who invented the simplex algorithm, which is a part of LPP in 1947. Terminology. So objective function, as we have already discussed, it is also mentioned in the form of an equation, right? So the equation in front of you, maximize 350 x1 plus 300 x2 is an objective function, where x1 and x2 are decision variable. It means that the value of x1 and x2 determines the value of the objective function. That's why they are decision variables, subject to constraint, right? So the inequalities mentioned the objective function are called as constraint. Why they are constraint? Because x1 and x2, the quantity of addition of x1 and x2 cannot exceed 200. So there is a limitation on the use of x1 and x2 here. So there is a limitation on the value of x1 and x2 together. So the together value, the addition value of x1 and x2 cannot exceed 200. So this is a limiting factor limitation, and therefore it is also called as a constraint. Then 9x1 plus 6x2 should not exceed 1566. 12x1 and 16x2 should not exceed 2880. So these are the constraint. And finally, x1 and x2 should be non-negative. So they should be either 0 or greater than 0. So this is how a linear programming problem is represented. So we have already gone through it. Yes. So xj is greater than equal to 0 for all 1 less than equal to j and less than equal to n. So linear program can be written under standard form. So this is the standard form. Maximize summation of j is running from 1 to n, and it is multiplication of cj and xj. So it is subject to constraints. So constraints are also represented in the standard form as shown in front of you. The problem is maximization problem, because we have written here maximize the objective function summation of cj xj, right? All constraints are inequalities. So constraints are inequalities here. So here you can see summation of aij xj less than equal to bi, and all variables are non-negative. So the decision variables should be non-negative, right? So they will be either 0 or greater than 0. So we have an example here, a resource allocation problem. A company produces copper cable of 5 and 10 mm diameter on a single production line with the following constraint. So there is a company which produces cable of two different dimensions, 5 mm diameter and 10 mm diameter on a single production line. So there are some constraints as well. So the available copper allows to produce 21,000 meters of cable. So the maximum quantity which can be produced by using available copper is 21,000 meters of cable of 5 mm diameter per week. A meter of 10 mm diameter copper consumes 4 times more copper than a meter of 5 mm diameter copper. So 1 meter of 10 mm diameter copper consumes 4 times more copper than the same length of 5 mm diameter copper. Due to demand, the weekly production of 5 mm cable is limited to 15,000 meters. So due to demand situation, the weekly production of 5 mm cable is limited to 15,000 meters, and the production of 10 mm cable should not exceed 40% of the total production. So cable are respectively sold 50 and 200 euros the meter. So this is the price. So what should the company produce in order to maximize its weekly revenue? Right, so define two variables here. So we define the decision variables which will determine the value of the objective function. So let x1 is the variable that represents the number of thousand of meters of 5 mm cable produced per week. X2 is the number of thousands meters of 10 mm cable produced every week. So the revenue associated with the production function will be z is equal to 50x1 plus 200x2, right? So this is the objective function 50x1 plus 200x2. Why 50 and why 200? So as written here, so cables are sold 50 and 200 euros a meter. So these are the prices of cable, right? So we multiply the quantities of x1 and x2 by the prices of cable 1 and cable 2 respectively to get the revenue. Right, so the revenue associated with the production is given as z is equal to 50x1 plus 200x2. So this is our objective function. So every organization will try to maximize the revenue obviously, and therefore this is a maximization type of problem. The capacity of production cannot be exceeded 21. So here it is written, the available copper allows to produce only 21,000 meters of cable of 5 mm diameter per week. So x1 plus 4x2 has to be less than 21, right? The demand constraint have to be satisfied. So x2 is less than equal to 4 divided by 10 x1 plus x2. So x1 plus x2 is the together quantity of x1 cable, that is type 1 cable, 5 mm cable, and 10 mm cable to be produced, and this should be the quantity of x2 should be less than 40% of the total production. So x1 plus x2 represent the total production, 4 by 10 represent the 40%. So x2, that is the quantity of type 2 cable, that is 10 mm cable to be produced, should be less than the 40% of the total production. So from this we get this equation, and x1 is less than equal to 15 as given. So negative quantities cannot be considered, so there is a non-negativity condition. So we cannot produce the negative quantities of x1 and x2, therefore x1 and x2 has to be greater than equal to 0. So we have a model now to maximize the sale revenue, that is the revenue. Determine the solution of the linear programming. So we have formulated a problem here now. Maximize. So we have to maximize the revenue. No organization would like to minimize the revenue. So we have to maximize Z is equal to 50 multiplied by x1, 20 multiplied by x2. So x1 is the quantity of type 1 cable to be produced, and x2 is the quantity of type 2 cable, that is 10 mm cable to be produced. 50 is the revenue, that is per unit price of the 5 mm cable, and 20 is the per unit price of the cable. So this is our objective function. This is subject to constraint. So x1 plus 4x2 should be less than equal to 21, minus 4x1 plus 6x2 less than equal to 0, as we have done. So this is from this equation we have calculated this, right? So minus 4x1 plus 6x2 less than equal to 0, and x1 should be less than 15. So this is from the situation given here, right? The available copper allows to produce 21,000 meters of cable of 5 mm diameter per week. Then a meter of 10 mm cable copper consumes 4 times the copper than a meter of 5 mm diameter cable. So from these all situations we have formulated this constraint and objective function. Now we have to solve the problem. Now the problem can be solved by two methods. We can solve the problem by graphical method, or we can solve this problem by simplex method. So large number of solution, the difficulty in solving this kind of difficult problem is the large number of solution. So there can be multiple solutions, but there can be alternative solutions, but not all the solutions are optimal. So we are here to find out the optimal solution, the best solution, right? The optimal solution. So choose the best solution among all the possible solution, right? So there are 2 raised to the power n number of solution. Why 2 raised to the power n? Because we have 2 decision variables x and y whose quantities are to be decided, and that's why 2 raised to the power n, or n factorial possibilities of all solutions. So there can be 2 raised to power n or n factorial possible solutions, and out of them we have to find out the best possible solution. So complexity of studied problem often NP is complete. So solving method, so we can use the graphical method or simplex method, or there can be approximations such as theory of duality and approximation algorithms. Let us study graphical method. So the constraints of linear program define a zone of solution. So when we solve this particular model, we have already seen, when we solve this model, this formulated problem, we get alternative multiple solutions, right? Multiple we can say solutions, a zone of solutions, but we need to identify the best solution also. So the best point of the zone correspond to the optimal solution. So there can be many feasible solutions which satisfies our criteria of limitation of factors, right? Constraint. But not all the feasible solutions are optimal, and therefore we have to find out the best point in the zone of solution, and that will be called as optimal solution. for problem with two variables, easy to draw the zone of solution and to find the optimal solution graphically. So when the decision variable consists of two, decision variables are two in number only, then we can use the coordinate axis, that is axis x-axis and y-axis, right, to find out the solution by graphical method. If there are more than two decision variables, in that case we have to use the simplex method. So in this case there are only two decision variables, x1 and x2, and therefore we can use graphical method to solve this problem. Alright, so what we have to do now, alright, what we will be doing, there are three constraints, right? This is a non-negativity constraint. Except this non-negativity constraint, apart from this non-negativity constraint, there are three inequalities, right? So these are the three inequalities. So what we do, we convert these inequalities into equalities. For example, x1 plus x2 is equal to 200. Then the second is 9x1 plus 6x2 is equal to 1566. Then we have 12x1 plus 16x2, this is equal to 2880. So what we did here, we converted all the inequalities into equalities, and what we are going to do with them now, so we are going to, these are our linear equation, right, equations of the straight line. These are all equation of straight line. So by using these equations we can draw the straight line on the coordinate axis. So we have this line x1 plus x2 is equal to 200, right? So how did we find out this? So we assume that when x1 is equal to 0, x2 becomes 200, right? So this is that point, 0 and 200. So when x2 is equal to 0, x1 becomes 200. So this is that point. So when we get 2 points, we can draw a straight line passing through them, because through 2 points there can be only one line which can pass through them, right? So there will be only one line which will pass through any 2 points in a plane. So by using this principle we get 2 points. When we keep x1 is equal to 0, x2 becomes 200 in this equation, and when x2 is equal to 0, x1 becomes 200. So we get 2 points on the coordinate axis, and by joining these two points we get a single line. This is a straight line which represent x1 plus x2 is equal to 200, this particular equation. Similarly, we draw equation for all the lines, all the remaining lines. This is 9x1 plus 6x2 is equal to 1566 lines, and there is one more, 12x1 plus 16x2, this is equal to 2880. So we have drawn all the lines of all the three constraints, right? Now we find out the overlapping area. So how do we find out the overlapping area? Now remember that all of these constraints were less than type constraint, right? Then we converted them into equalities in order to draw the equations, right, in order to find out the lines of equations, right? So all of them were less than equations. So when the equations were less than type, what we do to arrive at the common region or the solution region, what we do, we draw lines towards the origin from every line, right? And from every line we draw the lines like this to the origin, and the common region from all the lines we draw from all the these straight lines will be the common region. So in this case this is a common region when we draw these three lines less than type of constraint. So this is a common region. So this blue region is the common region. Okay, now your solution is not within this particular within this particular common region, but the vertices of this particular feasible region would give you the optimal solution. So you have to check the optimality of the solution at these 1, 2, 3, 4 and 5 points, 5 vertices of this particular polygon. So the optimal solution will always be there at the vertices. So we have to check at which vertex the solution is optimal. So by putting the same thing is shown here, the objective function, right? Okay, so by putting the values of x1 and x2 of these vertices, so here 0 and 180, right? So here the coordinates are 0 and 180. Here the coordinates are what is this line? Alright, so there will be some coordinate at this particular point as well. This is 0 and 0, so we find out the coordinate of this vertex also and this particular point also. So we find out the coordinate in the form of x1 and x2 of these points, and then we put the values of x1 and x2 in the objective function, and then we try to find out the value of the objective function, and when the objective function is maximum at any particular point, that particular point is the optimal solution. There is one more way to do that, and it is layout of line for objective function. So when we draw the objective function line, that is 350 x1 plus 300 x2 is equal to 35,000, right? So what we do, we try to keep moving this particular line towards outside, towards away from the origin, right, until it is in the feasible region, right? So now this particular line is now moving out of the feasible region, but it is tangent to one of the point of the feasible region, and this particular region is the optimal solution. What we did, listen, we drawn a feasible region. So what is the feasible region? It is the common region of all the three constraints, right? And how did we arrive at it? So we drawn lines from all the three lines. So these were the three lines which we have drawn on the basis of constraint, right? So we find out the common region towards origin from these three lines, right? And then what we did, we draw the line of the objective function as well as, and we tried to move it away from the origin like this. Look at the red line moving away. So we kept moving this line away from the origin until it is tangent to one of the point on the feasible region. So this particular line is tangent to this particular point of the feasible region, and therefore this is the solution of this particular method. So there would be some vertices in the form of x1 and x2 for this particular point. So by putting these values of x1 and x2 in the objective function, we get the maximum value of objective function, and it is 35,000, and it is the 52,500 actually. So this is how we can solve the problem by graphical method. So computation of the optimal solution. How do we compute the optimal solution? The optimal solution is at intersection of the constraint, right? So x1 plus x2 is equal to 200, 9x1 plus 6x2 is equal to 1566. So by solving these two equations simultaneously, we get x1 is equal to 122 and x2 is equal to 78. So look at this. So this is the point. So this is the point of intersection of two lines. So these are the two lines, x1 plus x2 is equal to 200 and 9x1 plus 6x2 is equal to 1566. So that was the intersection of these two lines. So what we did, we solved these two equations simultaneously, so by using simultaneous equation method, and we got x1 is equal to 122 and x2 is equal to 78. We put the value of x1 is equal to 122 and x2 is equal to 78 in the objective function. So this was our objective function, 350 x1 plus 300 x2. So we put the x1 and x2 in this equation, and what we get is 66,100 is the solution of the objective function. It is the maximum solution because at this particular point the objective function is 35,000, at this point it is 52,500, but this is the optimal solution which will maximize the revenue. So these values of x1 and x2, that is the quantities of 5 mm cable and the quantity of 10 mm cable to be produced, which will maximize the revenue. So this is the solution. So x1 is the quantity of 5 mm cable to be produced, x2 is the quantity of 10 mm cable to be produced. So when we find out these two quantities, we put these values in this particular equation, 350 x1 plus 300 x2, and what we get is 66,100 as the final solution. So thank you so much for watching this video. I hope you have understood and enjoyed this particular session. Keep watching the videos. Thank you.